Welcome to the presentation of the ECCV 2024 paper titled Sync from the Sea, Retrieving Alignable Videos from Large-Scale Datasets. This research was carried out by University of Central Florida and Adobe Research. It was led by Ishan Dave during his internship at Adobe, under the mentorship of Fabian Kaba, Mubarak Shah, and Simon Jenny. Before diving into the problem statement, let's first explore what video alignment is. Here we have two videos of tennis serving actions. Notice that key events, like the ball touching the racket, occur at different times in each video. This misalignment happens due to factors like varying start points of the action, differences in speed, or other variations in the actor's movements. These videos, therefore, are unaligned in time. Video alignment addresses this by synchronizing action phases, warping the videos so that key events occur simultaneously. In this example, we focus on three main events: the ball being released from the hand, the racket swinging fully back, and the ball making contact with the racket. The goal is to ensure these moments are perfectly aligned across both videos. Once these key events are aligned, the videos can be played synchronously, as shown in the bottom video. Now both actors are performing the same action phase at the exact same time. Video alignment has a range of highly useful applications. In this example, the top video shows a golf swing without any audio, while the bottom video includes the same action with an audio track. Our objective is to transfer the audio from the bottom video to the top video. However, simply copying the audio track from one video to the other isn't meaningful because the videos are temporally unaligned. To achieve this, we first need to perform temporal alignment of the visual modality. Once the videos are aligned in time, we can apply the same warping to the audio track and seamlessly transfer it to the first video. This way, the first video now has synchronized audio. This kind of transfer is also applicable to other video properties, such as animations and language captions. Now that we've seen how video alignment has valuable real-world applications in video understanding, let's talk about its limitations. Despite the extensive research in this field, most approaches assume that the video pair is already provided for alignment. In other words, they assume the videos are inherently alignable. For instance, in the previous examples, both videos featured the same action, such as a tennis serve. However, in real-world scenarios, we don't always have such paired data. This brings us to the research question: if we have a reference video, how can we find the most alignable video from a large dataset? That's the problem we aim to address in this work. Given a query video, our task is to identify the most alignable video from a set of candidate videos. Essentially, we evolve the conventional temporal alignment problem into a search problem, which we refer to as alignable video retrieval. Let's dive deeper into the problem statement. The first research question we tackle is, are regular video retrieval methods sufficient to find alignable videos? For some contexts, video retrieval methods typically rely on standard video understanding models, such as strong action recognition models. Consider this visual example. Given a query video of someone cutting a pineapple, the goal is to find the most alignable video from a large data set containing millions of videos. While traditional video retrieval methods provide semantically relevant results, such as the top 5 retrieved videos all showing pineapple cutting, they don't necessarily ensure temporal alignment. For example, in the query video, the actor first cuts off the pineapple's head, followed by the rest of the fruit. However, the retrieved results show different cutting styles and sequences, which are not temporally alignable. Only the third result matches the exact cutting style and action phase sequence, which is what we ideally want as the top result. To achieve this, we need to implement a re-ranking strategy to push the most temporally alignable video to the top of the search results. Before we propose a meaningful indicator of alignability for re-ranking, let's quickly recap the fundamentals of the standard alignment distance. The most common method to determine the alignment path between two alignable videos is dynamic time warping, or DTW. To compute DTW, we first construct a temporal similarity matrix by calculating the frame-wise feature distances between the two videos. Once these distances are computed, we identify the minimum distance path, starting from the first frame of both videos. By taking one step at a time, this approach follows a dynamic programming process. Ultimately, we obtain the minimum cost path, which represents the optimal alignment. The sum of the costs along this optimal path is known as the alignment cost. Although the DTW alignment cost is intuitive, it comes with some limitations. In this visual example, the video on the left is alignable, while the one on the right is not. However, if we look at their DTW costs, the alignable video surprisingly has a higher cost, which is counterintuitive. This occurs because the DTW distance is heavily influenced by the appearance similarity between frames, and the overall cost also depends on the length of the reference video. These factors can misrepresent the true alignment indication. To address this limitation of DTW when comparing alignable video pairs, we dive deeper into how the optimal cost is computed. In addition to the optimal path, we also generate multiple random paths that represent suboptimal alignments. The idea is to normalize the optimal path cost by averaging the costs of these suboptimal paths. This normalization helps mitigate the influence of visual similarity in video length, making the alignment costs more comparable across videos. We call this new metric Dynamic Relative Alignment Quality, or DIRAQ. When we apply this direct metric to compare two different video pairs, we see that it produces a lower score for the alignable pair than for the non-alignable pair. This is exactly what we need for a reliable re-ranking indicator. Now, bringing all the components together, here's how our system works. First, we retrieve the top K results using a standard video retrieval method. Next, we compute the direct score for each candidate video relative to the query video. Based on this score, we re-rank the results, placing the video with the lowest cost at the top. Finally, we retrieve the aligned video by applying the regular DTW optimal path. We propose cyclic consistency-based protocols to evaluate our alignable video retrieval AVR system. First, we propagate the ground truth phase labels to the top 1% retrieved result by warping the phases. Next, we propagate those phase labels back to the query video. Finally, we compute the cycle-back phase difference to measure the consistency of the alignment. In order to evaluate AVR, we report results on three datasets: Panaction, the combination of Panaction and UCF, and Kinetic 700. We consider three different frame-wise video representations for alignment. For the re-ranking metric, we first present results without re-ranking, directly from the retrieval method. We then compare this with DTW-based re-ranking and our proposed direct method. Our results show that direct consistently outperforms both of the other metrics across all protocols. As a minor contribution, we also propose a frame contextualization approach, which encourages learning better alignment features. The key idea is to provide temporal context by concatenating the current timestamp with the cumulative sum of features up to each time step. This method also helps reduce cycle errors across protocols. These improvements hold true for other frame-wise video representations as well. Here, we aim to understand the impact of our proposed frame contextualization on the standard temporal alignment task, using the well-established Panaction benchmark. Phase classification refers to the per-frame accuracy of predicting phase labels. This is achieved by training an SVM classifier on phase labels for each frame in the training set. Frame retrieval measures how many of the retrieved K frames share the same phase label as the query frame. Kindle tau is calculated across pairs of test videos by sampling 2 frames from the first video, retrieving their nearest corresponding frames in the second video, and determining whether their order is preserved or shuffled. For comparison, we reference expert methods in standard video alignment tasks, and also consider frame-wise self-supervised learning representations. When applying our frame contextualization approach to recent frame-wise representation methods, we observe consistent improvements over the baseline results. In this visual example, the top video represents the query, while the bottom video shows the aligned result retrieved from a search space of 500,000 videos. Across all top search results, key events are perfectly aligned with those in the query video. Our method also generalizes well to more diverse actions, as demonstrated in the rightmost video, where it successfully matches the action phases and interactions with dolphin. Our method demonstrates its effectiveness by aligning videos across diverse scenarios. For example, it successfully aligns the subtle movements of a coffee machine blade, showcasing its precision with small machinery actions. Additionally, it performs just as well on videos containing instructional content, proving its versatility in different contexts. In summary, we introduced the novel problem of alignable video retrieval ever, where we proposed direct as an alignability indicator, developed a cyclic consistency-based evaluation protocol. More interesting qualitative results can be found on our project webpage. Our method presents significant opportunities across various domains. In video representation learning frameworks, AVR can be leveraged to discover hard positive examples, especially in visual or multimodal settings, enhancing the learning process. AVR also proves useful for recovering labels from unlabeled data, whether dealing with limited, noisy, or incomplete labels, providing a powerful tool in semi-supervised or unsupervised learning. In video editing tools, it opens up new possibilities, such as recommending animations or audio tracks that align with visual content, and even enabling seamless caption transfers across videos. Lastly, AVR plays a crucial role in dense retrieval systems, such as RAG models, particularly in video-based large language models or diffusion models. This helps in efficiently retrieving contextually relevant videos to enrich generative models. Thank you.